All right, so it's the Thursday night webinar. We're going to cover Module 3, NOLI, and talk a little bit about Module 4. Let's see here. So here's the notes for Module 3. This is what's in. This is available on Blackboard under the Resources tab. So this is some data. It's a little bit older now, but this is some prices and size of random sample of houses sold in the 32301 zip code in Tallahassee. So there they are, the selling price in the house. So the first thing we might want to know is the sample size. In other words, the sample size would be how many houses we collected data for. So let's see here. Let me go ahead and get a pen here. So when the sample size is here, how many houses, how many individuals were there in the sample? So even though there's 14 numbers, or not 14, let's see, 6, 12, there's 24 numbers here, but that only actually represents 12 houses because each pair of numbers is one house. So like if I took this pair of numbers here, we might say that that's house 1, and so on. And then the next one would be house 2, and so on. So that the sample size is 12 houses. Okay, so I collected data on 12 houses. So then the next thing is the explanatory. And so we've talked about that a little bit before in Module 1. So we've got two variables here. One is the selling price and one is the size. Square feet is really you could say square feet is one of the variables, but that's really more of a unit. We're talking about the area of the house or the size of the house. So when you think about this, you want to think about, okay, which one of these influences the other? Well, changes in selling price don't generally cause changes in square footage, but changes in size probably make a difference in the selling price. So that means that the most logical explanatory variable then would be the selling price. So our selling price, and then logically that leaves as the I've got it backwards there. My apologies. The logical explanatory variable is the size of the house, and the variable that responds to that is the selling price. All right. And by the way, if at any point in time you have a question, just you can either click it into the chat box, or if you prefer to use your microphone, you can click the hand. Either way, I'll get an audio notification, which will let me know that you have a question. So like if I did something like that and got it backwards there momentarily, you could type something and say, that doesn't seem right, or something like that, or can you tell me why that is, especially if it's confusing to you. All right. Okay, so in order to see a pattern, it helps to draw a scatter plot, which plots each ordered pair as a point. We could draw the graph by hand, but we're going to do it on the calculator. So I'll pull up my calculator. My easiest way for me to do that is to just type in right there. So what you're going to see is you're going to see my calculator. So let's see here. Let's bring us. Oh, I didn't mean to do that. All right, so I'm going to go back to the previous page and then pull up my calculator so I can type this data in. So in general, what you want to do is you want to type the data into your calculator. And the best way to do it, what you want to do is you want to type one variable into each list. So I'm going to go into stat, press my stat key, my edit key, and then I'm going to go into, I got a lot of stuff in all of my lists. So I go up to the name of the list and I press clear, and the down arrow will clear that list out. So I'm going to put my data into list 1 and list 2. So then, so I'm going to just type each of these numbers, so bear with me for a moment. If you have your calculator with you, of course you can do the same thing. I'm going notice there that I forgot the dollar sign on the 145, but that's not critically important here. So it'll just take me a minute or so. There's not too many. I'm going to move my calculator so I can see the rest of the sizes. I can see all the selling prices. So you put all of the selling prices in one list. And then we're going to put the areas, the sizes, in another list. Next to that list. Alright, so it looks like we're good there. Alright, and I see here, if you see, hopefully you can see my little finger pointer there, it says L113, which means I'm on the 13th row of list 1, which means I've got 12 entries, which is what I want. Okay? Quick check to make sure you didn't miss something or type something extra in. Doesn't tell you that you typed in the right thing. So now I pressed the right arrow to go over to list 2, and now I'm going to type in all the various sizes. So the size of each house goes right next to the price that it's sold for, and that's really important. They need to stay together. The calculator is going to assume that they go together. And so make sure I get that in there. All right. So there we go. So I got my two numbers, and you see my lists end on the same spot, and the house's selling prices and the square footage are next to each other. So even though there's 4 rows in this table, that's just so the table didn't take up too much space. There's only 2 rows in my list, 2 lists, one list for all of the selling prices and one list for all the sizes. All right, so let's get this out of the way. So what we're trying to do is to draw a scatter plot. So let's see how we do that. All right, so I go into this. You hopefully are familiar with this from Module 2, but all the calculator graphs, all the statistical graphs are right above the y equals key. We hit the second key, and we hit the y equals key, and we get this menu right here. Okay, you can choose any plot. If you've done any practicing and you see any ons here, you should probably choose that particular plot. Mine are all 3 the same, so I'm going to choose plot 1. Okay. Mine are all off, and so the first thing I need to do is turn it on. I just hit enter while it's flashing on. Type is already set up for a scatter plot. It's the first one. If you did a box plot or a histogram and you need to change it, you just hit enter on the very first type. And then XList is where you put your explanatory variable. So for us, size is the explanatory variable, so I actually need to change that to list 2 because that's where I put size. I take the second button at the upper left and hit number 2, and that puts an L2 there. And I go down, and then list 1 is where my Y's, my selling prices are. I hit the second button and number 1. And then the mark is just how the points will be plotted. Personally, I think the little square, which is the one that's already chosen, is good. The far right one is just a single pixel. That's kind of hard to see. So now if I just press graph, I'm not going to get too much there. In fact, I have a couple of graphs there right now, which are from my other class. So I'm actually going to go into my y equals menu. And sometimes if you have something in there, it's a good idea to clear that out. The other thing I'm going to do real quick is I know one of the things, I don't want to see that, all those dots on my screen, so I'm going to type grid off there. All right, so, but now this is my standard window and my graph doesn't appear there. Well, a quick shortcut is to hit the zoom key and to go down to number 9. You don't actually have to scroll, you can just hit number 9 if you remember it. And there, because it says zoom stat, and what it does is it thinks you're doing a statistical graph, it looks at your data and it chooses a window that can display your data. So there's my picture of my data. Okay? As you might expect, as the size goes up on the x-axis, the home prices, the selling prices go up as well. So I can take a snapshot of that. Actually, I don't want to keep. All right, I'm going to go in. I just realized I'm going to change my window slightly. I might say, so my home prices, maybe I'll go from 750, that's just a little bit below where I was, to a little bit above that, maybe 2,500. And I'm going to mark my x-axis by 250. You don't have to do this, but it's going to allow me, when I put it in these notes, to put some stuff on there that makes sense. And here I might go a little below this, 65,000, and a little above this to 230,000. And then I might mark my y-axis. The y-scale is how often I mark my y-axis. Maybe every 10,000. Let's see how this looks. All right, so my y-axis marks are a little close together, but that's okay. Okay, so I'm going to now put this in the notes, so I can make it bigger and I can talk about it. Oh, didn't mean to do that. Oh, stop that. Another way. All right, so there's my graph. And so what I'll do is I'll mark real quick how I have my axes. So I think my selling prices went from like 65,000 to, I think it was like 230,000. All right, I can double check that. Oh. I'm going back to my window. Yeah, 65 to 230, and then the x's went from 750 to 2,500. So 750, 2,500. All right. So just like we did with single variable data, with single variable data we had some things we looked at about the distribution. We looked at the shape, the center, the spread, and the outliers. With two variable data, we did the same thing, only there's slightly different what we look at. We look at the form, the direction, the strength, and we look at outliers. So shape, center, spread, and outliers for single variable data, form, direction, strength, and outliers for two variable data. All right, so let's see. First of all, form. All right, what sort of forms can the data have? Well, really, what we're thinking about is what sort of pattern do our data follow? So clearly there's an increasing pattern, but that's actually the direction, not the form. The form is, if we were to use some sort of graph that approximated the data, what would the best type of graph be? So now there's lots of types of graphs, and college algebra, you learn a lot about those, but that's not a prerequisite for this course. So your thought is it could either be linear, like that, where a line models it pretty well, or, let's make that go away, or maybe curved. And you might make an argument maybe curved works in this case. But generally speaking, less linear looks like a bad model and it's obviously curved. Then our best bet is probably to go, if a linear model works, if a linear model works, then that's probably a good choice. So in this case, I would say your choices that you might choose might be linear or curved. And this one is linear. Or there might be no association at all. Or no association. Yeah. Okay. The next one is the direction. And basically direction can be positive or negative. Or if the curve doesn't solely curve up, if it goes up and then down, or down and then up, you might say the direction. Then the direction you might say is curved also. You can have a curved graph with a direction, like if you have a curve like this, that's a curve with a positive direction. If you have a curve like this, that's a curve with a negative direction. But if you have a curve like this, you might say it actually has a curved direction. So, but positive direction, basically you can think of it like a positive slope, or you can think of it as x goes up, y goes up. Okay? Negative is the opposite. So positive as x goes up, y goes up. Negative would be as x goes up, y goes down. And curved means as x goes up, we always think of x as increasing, we always go left to right. Y might go up and then down, or down and then up. Okay? And for this particular graph, this time I'm going to ask you, since you're on the call, the two of you are on the call, if you were to pick one of those directions, would you pick positive, negative, or curved? And you can jump in and use your chat box if you want to, or your microphone. There's just going to give it a go. Positive, yes, indeed. Okay, so it is positive. So we'll box in positive for this graph here. All right, now strength. All right. So strength is basically, right now it's going to be qualitative. So we're not going to numerically define strength, but we will in a little bit. But the question is, looking at that graph, is the pattern strong? Does it follow the line pretty well? Now you may say, well, the points are really scattered, but if the pattern is obvious, then it's pretty strong. We may not go as strong as very strong, but I'd say this is fairly strong. And again, this is sort of qualitative. So it's not like, okay, there's a right answer, but there's some obviously wrong answers. Like weak would be a wrong answer for this question, or not very strong would not be a very good answer either. I would say, like I said, something like fairly strong or strong. There, like I said, very strong might not be. We'll see when we get start numerically describing strength. Right? But for strength, I would say in this case, it's the question you might ask yourself when you're trying to decide strength: how closely does the plot follow the form? In other words, we chose a form of linear or curved. Does it seem to follow that form pretty clearly? Or another question you might have is, how obvious is the pattern? The more obvious it is, the stronger the association. So in this case, I'd say fairly strong or strong. But like I said, this is qualitative, not quantitative. In a little bit, we'll have more quantitative view of strength. All right. So looking at this, it says, do there appear to be any outliers? Was the last question. Okay, what do we mean by that? Well, when we say, do there appear to be any outliers, we mean, are there any points that deviate from the pattern? Are there any points? So there's two kinds of points. One is a kind of point that follows the pattern but is far away from the other points. And the other is a point that doesn't follow the pattern. So in this case, what we would mean by a point that doesn't follow the pattern is it's a bigger house that was cheap or a smaller house that was expensive. if we're talking about a point that's just far away from the other points, but still does follow the pattern, that would be a house that's much larger than the others or much smaller than the others. All right. So in this particular problem, I would say that there don't appear to be any obvious outliers. The points all pretty much follow the pattern. None of the houses is much larger than the others. There certainly is a largest house and a smallest house, but they are not, you know, way larger than the others or way smaller than the others. And all the points pretty much follow the pattern that bigger houses tend to be more expensive, the smaller houses tend to be less expensive. So, and in this case, I would say there are no obvious outliers. Oop, what happened there? There are no obvious outliers. Okay. Now, as far as the outliers go and whether or not they follow the pattern, a couple things to be aware of, and they mentioned this online, but an outlier that's far away from the other points in terms of the x value can have a very strong pull on the line. It can be, sometimes they even call it an influential observation. So if there was a really big house and it was really expensive, even if the pattern with the other houses was weaker, that really big, really expensive house would make the pattern look stronger. More importantly, if there's a point that really deviates from the pattern, like a big house is cheap or a small house is expensive, you might be interested in, is there something why that value deviates from the pattern? Was this a big house that's really run down, or was it a small house that has a lot of upgrades, that sort of thing? Or maybe the bigger house was sold to a relative. All right. Now, as with single variable data, we can use numerical summaries to determine some of these characteristics, notably direction and strength. There's a quantity called the correlation coefficient. The letter is R. It's a measure of direction and strength. We can use the calculator to determine it by actually going through this formula, but we're not going to actually do that. We're going to hold off on the calculation just a moment. So I'm going to scratch this out here. Right? You will see this in the on-site notes that are posted, but it's just going to give the R value. It's not actually going to show how we went through it. But basically what I did, I'll give you the quick 10-second summary. I found the mean of all of the sizes and the standard deviation of all of the sizes, and I subtracted the mean and divided the standard deviation from each home size. I did the same for each selling price, and then for each house I multiplied those two answers together. Then with the summation, I added them together, and then I divided by n-1. Okay? Don't sweat. You do not have to be able to apply that formula. Don't get nervous when you see that formula. But here's what you do have to know about what comes out of that formula. Probably, let's see here. The first thing actually is probably better to know is the third one on there. I probably should put that first. But that's okay. But the big thing is, start off with, is it ranges from -1 to +1, inclusive. And then we'll go back up to the top. In fact, maybe I can, well, I'm not going to, I don't think I'm going to, since I already have notes posted, I'm probably not going to post this. But it ranges from -1 to 1. And then the sign tells the direction. So if R is positive, the direction is positive. If R is negative, the direction is negative. It doesn't have any units, so you don't have to think what the units of R are. Now, here's the fourth one is where we really get important. If the absolute value of R is close to 1, so that means we don't really have to think about the sign for a moment. That would allow R to be close to 1 or -1, for the absolute value to be close to 1. The relation is more closely linear. If it's closer to 0, the relationship is, I'm going to cross out weak. This is actually bad work. the relationship is, well, actually, what I can do is I can say it's either weak or strongly non-linear. Okay, so if you had a very curved graph that went up and then down, that's not anywhere close to a line. So even though the R is close to 0, it may still have a strong association. It would just have to be non-linear. R only, so that's where the next one comes in. R only describes the strength of linear relations. So if you have a nonlinear relation, there's no point to finding the R value for it, the correlation coefficient. R is not a resistant measure. That means that it can strongly be impacted by outliers. We talked about the mean and the standard deviation were not resistant measures of center and spread. Similarly, R is not a resistant measure of the strength of a linear correlation. A single point can make it appear much stronger or weaker. This only works for quantitative variables. So it doesn't make sense to, like, say there's a correlation. Now we can say there's an association with qualitative or categorical variables, but not a correlation. So we wouldn't say there's a correlation, say, between college degree and income, because college degree is not a quantitative variable. And lastly, a really important one is that correlation does not imply causation. Even if two things are very strongly correlated, there may not be a cause and effect relationship. All right, so we will see some examples. In fact, let's now go and look and see some examples. I'll pull up a document here that I have. Let's see here. This is an old thing. I used to do this as part of that group assignment, but I decided it made the group assignment too long. So let's take a look. See if I can find it. Let's see if it's under. No, not under resources. There's quick look. Let's see if this is it here. Yeah, this is it, I think. Let's go down to right here. Oh, how did I go all the way back up? Let's just get my pusher told me a little help me. All right. So you see the one. So this gives you an idea of some scatter plots and what you would look like, what they would look like. The one on the upper left, it's pretty close to a line. It follows a line pretty closely, and the R is quite close to 1.943. The scatter plot 2, those points actually, if you do a line, it would actually pass through all those points. Let me see if I can get it. Let me get my pen here. Actually, let's see. Let's do some. See if I can get this. No, not good. I did the wrong thing. Shapes. That's what I want. There we go. All right. So if I do the first one. Whoa! I didn't mean to go up so far. Sorry about that. So you can see here that they follow that line pretty closely. But watch what happens with the second ones. Might be easier if I do it red. There we go. So let's do another one for these. And you can see the line ended up a little bit below the points, but the points follow the line exactly. So now on the third one, you can definitely see a positive pattern, but if I draw a line through there, the points are not that close to the line. They're not very close to the line. So the R is there is a little bit lower than it's 0.57. Okay. Let's go back. Let's do another one. Here, it's really hard to see much of any pattern at all, and you see the R is very, very close to 0. I almost started to say maybe there's an upward pattern, but I'm not sure that there is. I think When the r is close to 0, actually, it ends up making the line almost horizontal. Here, there's somewhat of a downward trend, but it's again not very strong. So maybe something like that on scatterplot 5. On scatterplot 6, quite a bit stronger. And you see the R is close to -1. Definitely a negative trend. All right, let's look at a couple more. Oops. Scatterplot 7, if I draw this line, this is another one where the points are right on a line. Oops, I don't know why it drops down after I draw it. But there you can see. And notice the R is -1. So when the R is 1 or the R is -1, the points follow a line perfectly. Right? And then the last one is a pretty strong pattern. But there is some scatter about the line. So the R is fairly close to 1, but not terribly close. So hopefully that, seeing those, gives you some idea of the pattern that the R takes. Okay, let's see here. Go back to my notes. My apologies, Iris, I can't remember if you've been on a call before. I do have a train track that runs through my backyard, so every now and then you'll hear a train whistle. Okay, so topic 3.2, linear regression. So you may recall that from your algebra classes that one way to find the equation of a line is to use 2 points. And you'll see in the notes that I actually do this example, and I could show you the idea. I don't think I'm going to go all the way through it because we don't have as much planner. Put this a little bit smaller. So maybe if I was trying to figure out the equation of a line through these points, actually I have a little line drawing tool here. All right, so maybe I would do something like that. It's hard to say exactly, but that might work. So I might actually choose, if I was going to pick 2 points, and these might have even been the 2 points I chose, that point and that point. And I might find the equation line passing through those 2 points. And if you recall from your algebra classes, you would find the slope of the line and then find the intercept, and that would be the equation of your line. So you get a line that is y equals mx plus b, right? And we could even, maybe I should go ahead and pull up the notes here and show you the line, but so we can actually, well, what we're going to do is we'll go ahead and get the regression line, and that's on the next page here, and then we'll use that and we'll go backwards for a moment and look at the idea of the residuals. So this says use your calculator to find the equation of the least squares regression line that best describes the data. So the regression line is just, as it says, is the best sort of, you might call it, sometimes it's called the best fit line, right? So I can get this from my calculator without actually having to do any detailed work. So I'll hit second, quit. Oh, I missed it. I missed the second, the quit button, second. There we go. That always takes me back to my home screen. So what I do to get this equation is I hit the stat button, and I go to calc like I did for the 1-bar stats in the last module. And then I'm going to go down to either choice 4 or 8. 4 and 8 do the exact same thing. I have a preference for 8, which I'll explain in a little bit. But 4 is fine. Most students prefer 4 because they remember a line as y equals mx plus b, and 4 has that same form. Form 8 is if you wrote the b first and then the mx second, b plus. Which way you choose to write that is not terribly important. So, but I'm going to choose number 8. So that's what it says. You can hit enter here, but this is the wrong answer. You have to tell the calculator where the x's are and where the y's are. I put my x's in list 2, in fact. Often your x's are in list 1 and your y's are in list 2. But in my case, if I hit second and 2, I'll get L2, hit my comma, hit second and 1, and get my L1, which is where my y's are. If you don't put anything, the calculator is automatically going to try L1 and L2 in that order, which for this problem would be backwards. And sometimes if you had them in totally different lists, you would totally get, you might even get an error message. So I apologize that I should have turned off my email notifications for the webinar. They keep popping up. So hopefully nothing too embarrassing will come over there. Let's see here. So now I just hit enter. After I do that, I hit enter, and now I get the equation of my regression line. Now you see the R is now there at the bottom of the screen. If you're following along and you don't have that R, it tells you how to do it on the calculator video. It also tells it to you, I remember now, at the very beginning of the assignment sheet, the assignment description, so you can get it there. But if you're watching the video and you don't want to go there, if you hit second and the 0 key for catalog, second and the 0 key, we want to go down to the D's, and the key with the D over it is the x to the -1 key. So I don't even have to hit anything because the little A is in the upper right hand side of the screen. So I just hit the x to the -1 key, it goes down to the D's, and I'm going to scroll down a little bit and look for something that says diagnostic on. Let's see here. Diagnostic on, hit enter, and hit enter again, and once it says done, then every time I do a regression, it's going to give me that R squared and R. So let's try it again. Stats, calc, 8, second and number 2 for list 2, comma, second and number 1 for list 1, and hit enter. All right. So I'm going to go ahead and write down the equation of this line. Let's see. It looks like I'm going to have to write it in 2 parts. Y. I'm going to put a little symbol over the top of the Y there. Y hat equals, and it was 3437. I don't need to go to decimals because that would be saying it matters how many pennies the house is. And then I will do decimals on the slope though, because I'm going to be doing thousands of square feet, and that'll multiply those decimals out. So I'll do like 90. You could do 90.4 or 90.36 for the slope. I'll do 90.4. That should be close enough. Plus 90.4x. So that's the equation of my regression line. That's the equation of my regression line. Okay. So now it talks about the sum of squared residuals. What is a residual? I'm going to go back to the previous page where it actually talks about what a residual is. It says the residual for any x value is given by the actual y value for that x minus the predicted y value. Well, you have to know, so you can determine residuals for any of the points on your graph. Well, I need to know the coordinates of those points. So if I go back to the very beginning, of those points. So basically, I can get a residual for any of the houses that I had. So let's pick one. Let's pick the house that was 1,600 square feet and $145,000. So what I'm going to do is I'm going to take my calculator. Let's do it over here to the right so I can see what I'm looking at. All right, so I'm going to do, I think I said 3437 plus 90.4 times 1,600 times my x. right? And my predicted selling price is about $148,000. Most houses sell for some multiple of $1,000, sometimes for $100. A couple of these, well, just one, the one that was $159,900. All the rest sold for an exact number of thousands. So it would be fine to say that the approximate selling price is $148,000 or $148,100. Okay, but the actual selling price of the house was $145,000. So what I actually do is to find the residual is I take that $145,000 and I subtract off the $148,000. It's okay to be a little more exact for the residual. And I get negative $3,077. And what that basically means is that there was a predicted selling price of $148,077, but the house actually sold for a little over $3,000 less than that. So we'll go ahead and I'll write that down. There we go. So let's just say here, for the 1,600 square foot house, square foot, and put X here, that's what that is, house, Y hat, since these numbers above were rounded, I'm going to put Y hat is approximately equal to $148,077. So that Y hat, the reason why I use a Y hat there is because, just like it said on the previous page, this is a predicted value for Y. You may say, well, why would I want to predict a value for Y for 1,600 square feet? I have a house that sold for that sold it at that size. Well, if another house came up for sale, and you wanted to predict what the selling price of that house would be, you would use the model rather than the 1,600 square feet house, because the model takes into account all of the houses that were sold in my data set. Whereas it wouldn't make sense to say, well, every 1,600 square foot house should sell for the same amount. It would make more sense to make a model based on lots of different houses and use that model to determine the selling price for a new 1,600s in the market. So then the residual, as it showed on the previous page, the residual is Y minus Y hat, which Y is the actual selling price, so that was $145,000. 145 minus 148,077, which was negative 3,077. So this house sold for $3,000, a little over $3,000 less than we would expect a 1,600 square foot house to sell for, based on the data set we have. Now, what does it mean by the sum of the squared residuals? That means if I calculate that residual for all 12 houses and then squared each number and added them all together, it turns out that the least squares regression line, the definition for that, is that it would have a smaller sum of squared residuals than any other line. So basically, the residual, you can think of the residual as the prediction error, how much the prediction was off by. So if you square all those, the negatives and positives don't cancel out, add them together, the least squares regression line will have the smallest possible sum of squared residuals. And the calculator, if I pull the calculator back up, it actually, every time you do a regression, it actually gives the second key in stat for the list menu. You'll see right there at the bottom is the residuals. And so I could figure out that sum of squared residuals. It's not something you need to be able to do. And you may see an example of it in the OLI, but you don't need to actually calculate the sum of squared residuals. Just understand that what makes our line the best is that it has a lower sum of squared residuals than any other possible line. All right. Now, the next question, important one, what do these numbers from the equation tell us? A little bit higher. In other words, can I interpret the slope and the y-intercept? Okay, so first the slope. Well, first of all, you have to remember your y equals mx plus b, and that the slope is the number with the x. So in this case, the slope is 90.4. Well, in general, the slope tells us the change in y for every change in x. So in this case, I'll write the general slope equals the change in y per change in x. All right, and so in this case, that's the change in selling price, predicted selling price, because the equation is about predicted selling price, not actual selling prices. The predicted selling price per square foot. Okay, which is $90.40. So we expect that the predicted selling prices go up by about $90 per square foot. Okay, so that's if we wanted to actually talk about our prediction, our interpretation, we'd say predicted selling price increases by about $90 for each added square foot. You can say per square foot is fine. And you'll see if you read the notes that I posted online, the on-site notes, it adds a little something to that. It says that slope tells what happens to y, well, to y hat, the predicted y, when x goes up 1. So when x goes up 1, that means that that's the added square foot. For each additional square foot, the predicted selling price goes up by about $90. Okay. What about the vertical intercept? You may remember from your algebra classes that the y-intercept or vertical intercept is that's where it crosses the y-axis, but in terms of the coordinates, that's where x is 0. So this basically says a 0 square foot house to sell for $3,437. So I'll write that, but then I'm going to mention something about that. So a 0 square foot house would be predicted to sell for $3,437. But of course, first of all, you can't have a house with 0 square feet. One of my clever students once said, well, does that mean that's the predicted price for a vacant lot? And that's a pretty good for a possible interpretation, but even that doesn't really work, because the problem is that you would need houses going down closer and closer to that 0. So in this case, the interpretation doesn't really have a meaning in that sense. So in this case, I'm probably not going to ask you a question where it doesn't actually have a meaning. So you can say, I'll add this, no real. Let me see if I can write that a little neater. No real meaning. Be quiet. So either you're really understanding this stuff, or you don't know what to ask, or you're not brave enough to ask questions. So I'm going to pause for a moment in case you have any questions. That's the whole. That's your benefit to coming, as opposed to just watching it online. So any questions as of yet? And because otherwise I would just post a video and not bother with having webinars. All right, nobody's responding, so I'm gonna. Oh, here comes one, maybe. But please don't. I don't want you to, like, if there's something that goes past you or over your head, I don't want you to let me keep going. Click the chat for a question, or click the hand, whatever it takes, get my attention, just like you would if you were in a classroom. Again, that's your benefit to attending the webinar as opposed to just those who might watch the video or those who don't do it at all, is that you're the ones who get to ask questions. I'm lost. Okay. So let me just sort of summarize where we are. There's not a lot left, so let me sort of summarize where we are at the moment. Where we are is, so we have a set of points. Okay, we graphed them because we wanted to see if it seemed like there was a relationship between the two variables. When we graphed them, it looked like there was a relationship, a positive relationship. And it looked like a line would do a decent job following that relationship. And in fact, I realized I forgot to graph the line, which I'll do in just a second. So it would be nice to have an equation, since there seems to be a relationship. It would be nice to have an equation that would allow us to use an x value to predict a y value. And that's what our regression equation is. It's an equation that allows us to predict the y value based on x value. To the calculator. So let's actually type that equation in here into our y equals. I just pressed the y equals button. So if I did 34, 37 plus 90.4x, and then if I graph that, you'll see that these are that's the line that we came up with, our regression line. It does a pretty good job of following the path. So this is a pretty good regression line. And then from that point, what we do is we would then, if we wanted to, use that line to predict different values. Okay. All right. So that's sort of where we are. And the other thing is remember, if you have an R and you're trying to decide what that R tells you about the strength, you still have to look at the graph. That's very important. All right, so let's go back to the notes. Hopefully that gets you a little bit back up to speed. So it says use a regression equation to predict the selling price of a house that is 1,200 square feet. All that means is plug in 1,200 for x. So I would do what I did on the other example. So I have y hat equals, and this is 34, 37 plus 90.4 times 1,200. Right, and you do that with the calculator. So I have to go back to my home screen. Well, I could actually, here's a little trick on the calculator. If you hit the second button, and then if you do it a second time, it brings you the line before that. So that way I can just change that to 1,600 to 1,200. And I have about $111,900. Rounding it to the nearest hundred is plenty accurate enough. So it's about $111,900. Now it says, how does it compare with the actual data? Let's go back and look at our data table. It's right here. Okay, so
It says how does it compare with the actual data? Well, that made me think that it asked me to find a residual, but there wasn't an actual house that sold that was 1,200 square feet. So I actually can't. There is no data to compare it to. So there was no 1,200. But we did it for 16. All that would mean, basically, this means compute the residual. Comparing it to the actual data means compute the residual. Okay, but in this case, there was no 1,200 square foot home. So there's nothing to calculate. Okay. But we did it for 1,600 square foot home. If we go back a page, there it is. We predicted the selling price of a 1,600 square foot home. And then we calculated the residual. And that was, so the actual house sold for about $3,000 less than predicted, $3,100. All right, so that's all we need to do on that one. All right, now it says use the regression equation to predict the selling price of a home, which is 4,000 square feet. So same idea. I'm not going to write that down here. I'm just going to go into my calculator. I'm going to hit second, hit the enter key, and change 1,200 to 4,000. Okay, and that's 365,000. That's a really expensive house, right? About 365,000. All right, but notice if we go back to our data, the largest selling price in the data largest house in the data was 2,165. So this house is almost twice as large as the largest house in the data. So, and then the selling price was far more expensive than anything. So this house was much larger than any house in what this means is the prediction is not reliable. So prediction is unreliable. Because here's the deal, I don't have any houses about that size to compare it to. So if I go back to my calculator and I go back to my graph, I have no way of knowing that this pattern continues for larger houses. There's no way to know that. And thus, I can't make a good prediction about that house. If I had a lot of some other larger houses, I might be able to more accurately predict this house. So in general, you shouldn't use the equation to predict for x's that are larger or smaller than the ones in your data set. The x's you use should be basically between your smallest x value and your largest x value. That's something to be really aware of. This is called extrapolation, and you don't want to generally do it. So using x values outside of the range of the data is called extrapolation. And should be avoided. So that's something to be extra cautious about. All right, last couple of things. One is the R squared. That number R squared that our calculator gave us, it's not there anymore. Let's go get it. We can just do it the linear regression again.
So we'll get it again. So the R squared was about 0.66. Oh, and we actually didn't mention that R that we got either. The R was 0.81, so that's fairly strong. It's not super strong. Basically, really strong relations are like between 0.9 and 1, or negative 0.9 and negative 1. And then fairly strong relations are 0.7 to 0.9, and then somewhat weak, but still useful strength is 0.5 to 0.7, and below 0.5 R, it's pretty weak. But the R squared actually, in some ways, is even more important than the R. What this tells us is, and it's kind of a little bit of a complicated concept. The idea is here, 66. What we can say is this. We can think of that as a percentage. 66% of the variation in selling prices. Okay, so I'll pause there for a moment. The selling prices are all over the place. There's a lot of variation. They aren't the same. So what causes that variation? Well, what we can say is that 66% of that variation is related to the size of the house. Okay, so the fact that the houses are different sizes accounts for the fact that they sell for different amounts. It accounts for 66% of that variation. Right? That means there's other things that also affect the variation. Things like the condition. So here's some other things. Condition, age, which is kind of related to condition, lot size, how big the property that it's on is, school zone, even though two houses may be in the same zip code, they're not always zoned for the same elementary or middle or high schools. So those are some other things to be aware of. So that anytime you're thinking about a relationship between two variables, you should also think about other variables that are related to those two. That sort of finishes up Module 3. Unfortunately, we didn't really, let me see here. Yeah, that's kind of the end of our time. We didn't get too much to we didn't get it all to Module 4. That's most of what I wanted to say in Module 3. Let's go for some. Oh, and then the other thing, the last thing here is many variables are correlated but do not have a direct relationship. What are some examples where correlation does not imply causation? There's all sorts of examples, but one famous one was where they found that children who took music lessons young had better grades in school, but there's a correlation there between music lessons and grades, but that's not necessarily meaning that it's a causation. Perhaps kids who take music lessons come from better off families, and that is more the cause than the music lessons. So there's also an example on OLI as well. Very, very quickly though, the one last thing I will mention Module 4. I'll try to give you like a 2-minute synopsis. It's just a different type of relationship instead of being linear. It's what's called an exponential relationship, and it looks like this: y equals a, or y hat I should say, equals a times b to the x. And basically, linear means you add the same amount each time or subtract the same amount each time. Exponential means you multiply by the same amount each time. And the a is sort of like the y-intercept, and a linear initial value, or the y-intercept. The b is called your growth or decay factor, depending. And how do we tell whether we're growing or decaying? Just from the equation.
course, you can tell from the picture what it's going to be, but the relationship between the B and whether you're growing or decaying is when you multiply by something bigger than 1, your answer is bigger still. So like if you multiply it by 2, of course, you're going to get a bigger answer. But if you multiply by something smaller than 1, like 1/2, you're going to get a smaller answer. So B greater than 1, that indicates growth. And we only work with positive numbers here. If 0 is between B and 1, if B is between 0 and 1, that's decay. And then the last thing I'll mention is that you can determine the percent growth or decay from that B, basically by the difference with 1. And this is explained in OLI as well, but like if B equals 1.05, you would do 1 minus 1, or 1.05 minus 1. That equals 0.05, which is 5% growth. So you always just subtract 1. But if B equals, say, 0.75, we do 0.75 minus 1, which is negative 0.25. That indicates 25% decay. So whatever that B is, whatever that growth or decay factor is, you can subtract 1 from it, and then change that decimal to a percent if it's positive. So basically, if it was greater than 1, then that's whatever the percent growth is, and if the original B was less than 1, that's going to be decay. So that should be enough to get you started. Oh, and then how you get the equation would be still go stat and calc, and you would just go down. I think it's number 9 is exponential regression, and there's a video on that too. Oh no, that's lower than. There you go. Letter 0 or number 0 is the exponential regression. So if you do that, even if I did it, let's say here, let's say I was curious if there was an exponential relationship between my two variables. There's my R and R squared. My R squared is actually a little bit stronger now. The R is, remember I said R is only for linear relationships. Don't worry about how they got one for an exponential right now. They did, there's a sort of transformation. But you'll see that if I'm looking at it as a percent growth per square foot, it's very, very, very small. This is definitely a different model. If we try to put that in there, let me see if I can kind of write it down so I don't forget it. If we put it into the y equals to look at the graph, it's 47965, 47965. Let's put the 0.5 in there. Times 1.000, and I'll do 684 to the x. So the way I would type that in my calculator is 47965.5 times 1.000, 684 raised to the power of x. Let's see what that looks like. So it's not that doesn't make a strong curve, but it definitely is different. And it looks marginally smaller, 70% instead of 66%. And is a simpler model, so if they're pretty close, a lot of times the line is the better choice. All right, I think that kind of wraps up what I want to say. I don't want to keep it too late, but I know it's a lot of information to digest. Hopefully, after you go through OLI again, look at the printed up on-site notes that I've posted, you'll have a better feeling of how to tackle the quizzes. And again, if you got questions, post them on OLI, so that, or sorry, on Piazza, and I'll do my best to answer them. I will have the Monday sort of office hours question and answer session as well if we've got some last minute questions. Oh, actually, sorry, I won't do it Monday because that's a holiday. I'll probably do it Tuesday of next week for the next webinar. Any questions before we wrap up tonight? Like I said, I know a lot to digest. All right. Well, thank you too. And again, if you do have questions, please ask, and I'll do my best to answer them. And I will